Hello there. This lecture is all about graphs, charts, and tables, and how you use those tools to describe your data. So as you can imagine, it's difficult to make sense of large amounts of data. So you can place this data into tables or charts. The type depends on the nature of the data, but we'll talk about that in a minute. Anyways, you can place your data into tables or charts, and that'll give you a visual of the trends and the distribution and characteristics of whatever it is you're measuring. So I'm going to go over a lot of the tools that you can use to simplify your data without just having to look at a big old jumble of numbers. So this is what you can expect out of this lecture. I'm going to start off with different ways to display cross-sectional frequency-based data. Cross-sectional meaning that it was data that was collected in a single time period, and frequency meaning that we are counting the amount of something in our data. Then I'll move on to displaying time series data, which is just data that was collected over a series of time. And when you do that, sometimes you want to delineate the data based on the time period it was collected, and I'll show you how to do that using tables and graphs. Then I'll move on to displaying non-frequency based data. Specifically, I'm going to be looking at scatter plots, which is the foundation for correlation analysis. Unfortunately, we don't cover correlation in this class, but if you know anything about correlation, then you'll recognize the types of things we're looking at with scatter plots here in a little bit. And then finally, I'll provide you with a table that just outlines when to use what. So in what circumstances is it appropriate to use what types of tables and what types of graphs to display your data. So this first section, looking at cross-sectional frequency-based data, is going to cover quite a few different types of tables and graphs. Of course, this isn't an exhaustive presentation of every way that you can display your data, but it is a summary of the most common types of frequency distribution tables and graphs used in the business world to display data. So this first is just a simple frequency distribution table. So at the top of the screen there, you can see the raw data. So this is data looking at, in the past 50 days, how many iPads were sold. And each number there represents one of the days in our data set. So if you feel like counting, you can see that there are 50 numbers up there. Each number represents a day, and the number tells you how many iPads were sold on that particular day. So if you look at the frequency distribution table below, you can see how that's constructed. So what you do is in the first column, you provide the label for what's actually being measured. So in this case, we're looking at the number of iPads sold per day. So that's our first column. And in that first column, you want to represent the full range of values in your data set, from lowest to highest, top to bottom. And be mindful of that. Let's say, for instance, there was a 7 in this data set. Well, then that first column would go from 0 to 7. Now, let's say that that 7 is entered in the data set. Well, there are no 6s. You still include the 6, and then in a little bit I'll show you about the frequency-based column. You would just put a 0 for the frequency for that. So even if you have a value that's not in your data set, but it's within the range of values that you have, you want to include it in that first column. Now, sometimes this first column is labeled as X. X is just a label as a placeholder for a variable of interest. And then this next column, the one next to the number sold per day, this represents the frequency of the values in your data set. In this case, the frequency represents the number of days. So how many times, if I'm looking at that raw data at the top, how many times do I see each one of these values in my data set? Or in other words, how many days did I sell a particular number of iPads? Sometimes you'll see this column labeled as F. F stands for frequency. So if we look at this data, let's start with the first row here for 0. 0 iPads sold in a particular day. If you go up to the data, you can see that there are, so 1 in the top row, so 1, 2, 3, 4, 5 zeros in that data set. So you just put a 5 in the column next to the 0. So looking at this table, we can see that out of all 50 days, we sold 0 iPads 5 of those days. And you just do the same thing all the way down. So there are 8 days where we sold 1 iPad. There are 14 days in this data set where we sold 2 iPads, 13 days where 3 iPads were sold, 6 days where 4 iPads were sold, and 4 days where 5 iPads were sold. So now, just as a quick check, you can make sure that you have done your math correctly because it is easy to sometimes forget to count one of the values up there. You can add up the frequencies, add up the number of days, and make sure that it equals the sample size. Now, even if the sample size, which in this case is 50, isn't given to you, you can count the number of data points and make sure that it adds up to the number that you get when you add up all the frequencies. And in fact, it does. So you can see that if we add 5 plus 8 plus 14 plus 13 plus 6 plus 4, we get 50, and there are 50 days in this data set, so I'm feeling pretty good that I did this correctly. Now, one thing that I do want to point out, and this isn't often presented in a frequency distribution table, but it will show you how to use a frequency distribution table to make calculations easier. So in the next lecture, we'll be talking about measures of central tendency, and you'll need to be able to calculate the sum of x, or in other words, the total amount in our data set, the sum of all the scores if we added them all together. Now, you have to be careful. If your data is presented in a frequency distribution table, you can't simply just add up all of the x values. So you can't say, oh, well, number sold per day. So 0 plus 1 plus 2 plus 3 plus 4 plus 5. That's not going to give you the sum of x. It's not going to give you the total number of iPads sold in this data set. In order to get that number, you have to take the frequencies into account. So you have to say, okay, well, there were 5 days where we sold 0 iPads. So 0 times 5 gives me 0. There were 8 days where we sold 1 iPad. 1 times 8 gives me 8, and so on and so forth. And you'll see the calculations in that XF column on the far right. Now, you get 119 once you multiply each X times each F, so each value times its respective frequency, and then add down. And you can also get that if you just go up to the top of the raw data and you add 4 plus 5 plus 3 plus 2 plus 1 plus 2, all those numbers together, you will also get 119. Again, you can't just add up the X column, you have to take the frequencies into account, and that should make sense if you look up at this data. At the raw data, we're not just going to add 1 4, there are 6 4s that would be included in that calculation. Now, at this point, you may be a little overwhelmed by the XF column and what that all means and how to do it, but I assure you, if you get comfortable with this method, it'll save you time, because if you're given large amounts of data and you need to do calculations, it's going to be a lot easier to make mistakes, and it's going to take a lot more time if you're using all that raw data and plugging all those numbers in for calculations than it is to use the simplified calculations in the table. And who knows, you may get a situation where you don't have access to the raw data and you need to make calculations. So before I show you some different frequency distribution graphs, I think it's important to talk about what the contents of a frequency distribution graph are, and then to talk about different shapes that can emerge when you plot your data in a graph. So first things first, the x values, remember that's sometimes what your actual variable values are labeled as, the variable of interest. Those x values can be represented along the horizontal axis along the bottom of a graph. And that'll be from the lowest score to the highest score, from the left to the right. And you'll see plenty of examples of these. Now the frequencies are represented along the vertical y-axis, so going up and down. And that axis starts from 0 and then goes up to the highest frequency from the bottom to the top. So think about that when you look at these pictures. So for the normal curve, the first one on the left, you'll see that the bulk of scores fall right in the middle. So you can see, there's that peak in the middle that represents the highest frequency of scores. Then as you get to the high end to the right or the low end to the left of this, you can see that there's less frequently occurring values that are high or low. So you can call those outliers on the end of your graph there on either side. Just more rare occurring values. Now, the rectangular distribution is just a distribution where every single variable occurs the same frequency. So, kind of a silly example would be if I measured the number of eyes among everybody in our class. Everybody has 2 eyes, I'm assuming, so we wouldn't have any variation in our data, and we would have a rectangular variable. So both of these distributions are symmetrical distributions. Symmetrical means that if you drew a line down the center, the middle of the distribution, and you folded it in half, you would have a mirror image on either side. So you can see for the normal curve, if you drew a line right down the middle from the high point down to where it says variable, you could fold that in half and see the same thing on either side. Same thing goes for the rectangular distribution. Now these are also unimodal. You'll learn all about the mode in the next lecture, but mode is just the most frequently occurring score. And you can look at this graph and you can see, oh, there's one value for the normal curve that is clearly the most frequently occurring. There's one peak in your graph. For rectangular, there's really no mode here. You could say unimodal. There's only one score that occurs the same frequency if you're looking at number of eyes, but in general, there's really no mode here. There's no clear value that occurs more frequently than any other. Now these are also symmetrical, but these are multimodal shapes. So the bimodal, you could fold it down the middle and you would see, if I was a good artist, you would see a perfect mirror representation on either side. Close enough on this screen. And there are two values in your data set that are most frequently occurring. Then on the right, you see the multimodal. Well, there are more than two values that are most frequently occurring in your data set. Now, sometimes you have non-symmetrical distributions in your data, and these both represent a non-symmetrical unimodal shape or a skewed shape. So this first one on the left, the negative skew, the bulk of scores are higher, so there's more frequent higher values. Remember, when you plot your x-axis, it goes from lowest to highest, left to right. So your higher values are around this peak in the negative skew, and then the tail goes off to the left, or the low end of the distribution. Whereas the positive skew, the bulk of scores are in the low end of the distribution, and then you have some values that are in the high end but not as frequently occurring as those that are in the low end. Now some people have difficulty remembering positive versus negative skew, and I always think about if I flip it over, if I turn it over, if it looks like a P, then I know it's a positive skew. So if I, start from the bottom left corner and flip it over on its side, it looks like a P, P for positive, positive skew. You can also think about it in terms of skew refers to the tail. Positive, you can think about the high end of the distribution, tail to the high end. Negative, skew, you can think about the tail, negative, the low end of the distribution. Whatever works for you to remember the difference is fine with me. So let's go ahead and look at a frequency distribution histogram. So there are two primary ways to display data using bars. One is a histogram. And a histogram, the bars touch halfway and above and halfway below the particular response option or value in your data set. Now you'll look at a bar chart here in a little bit and you'll see the difference between the bar chart and the histogram. So the histogram, the bars touch, and a histogram is only appropriate for interval or ratio data, so data that's quantitative or numeric in nature. And you can look at this for this data because we're looking at the number of iPads sold per day. So that table that we've been looking at. This is a ratio variable because number of iPads sold, you know not only the magnitude of the difference between each value, but you also know the direction of the difference. So for example, if you sold 2 iPads in a given day, not only do you know that you sold more than a day where you sold 1 iPad, but you know you sold 1 more than a day when you sold 1 iPad. So you know how much, and you also know the direction of the difference. Now, it's ratio data because there is a true 0 point. 0 means a complete lack of iPads sold. So we would want to use a histogram to display this data. So remember I mentioned before, the x-axis represents the different values in your data set. Make sure that you label your axes not only with the numbers, but also with the label for those numbers. Because if you're presenting this data to somebody, they need to be able to understand pretty clearly what they're looking at. So you'll see along the bottom there, the x-axis, the number sold per day, and then each value for the numbers sold per day in my data set, represented from lowest to highest, left to right. Now the height of each bar corresponds to the frequency associated with each number of iPads sold. So you can see that first row in the table, 0, there were 5 days where we sold 0. Go to 0 on the chart, and you can go up to 5 on the y-axis and see that that height corresponds to the 5 days where we sold 0 iPads. Now, I mentioned bar charts before. Here's a picture of a bar chart. That's used for nominal or ordinal or more qualitative data. And in this example, we're no longer looking at how many were sold per day and how many days did we sell that many. We are looking at a single week. So before we were looking at 50 days, now we're looking at a single week, each day of the week, how many were sold each specific day of the week. So now the variable that we are counting, essentially, variable that we're looking at and looking at frequencies for, is the day of the week, and that is an ordinal variable. It can be placed in a meaningful order, but it really doesn't have any numeric quality to it. So if you look at the bar chart, you can see that whereas the histogram, the bars touch, in a bar chart, they do not touch. Now I do want to point out, let's say for instance that there were no days where we sold 3 iPads. Well, then the bar for 2 and 4 would not touch because there would be no bar here. It would just be right down here to 0. That's why it's important to represent the full range of scores in your data set. Okay, so if we're looking at this bar graph or bar chart, you can see the bars don't touch, and just like before, we label our x-axis with the different values in our data set, in this case the different days, and then the y-axis represents the frequencies, in this case the number of iPads sold. The height of the bars corresponds to the frequency associated with each group along the x-axis. And just to make sure you understand what the contents of the frequency distribution table are, you can add up these values here, the number of iPads sold, add up the frequencies, and that gives you the sample size. We've got 19 iPads that we're interested in. Whereas here, we had 50 days that we were looking at. Okay. So one useful thing about putting your data in this form is to not only identify the shape of your distribution. So this one would be pretty close to normal, whereas this one is pretty clearly a negative skew. Most of the iPads were sold on the weekend, and then you've got your skew to the low end of the distribution, or the early end of the distribution if you're talking about days. So you can identify the shape, but you can also identify the center and the variability of your data. So in this case, we can say most iPads are sold on weekends, but there's not really a huge difference. And for variability, that's really looking at the spread of scores in your data set. And we can say, yeah, there's some differences, but there's not a huge degree of variability in the number of iPads sold. There's no day where it's just like, oh my gosh, there's so many more sold on this day than others. There's really not much of a range in our data set. Whereas here, same thing. You can see that, the bulk were sold, the bulk of the days we sold 2 to 3 iPads, and there's not a whole lot of difference among those days. There's not any outliers. Maybe if we had a situation where, I don't know, maybe we sold 0 on 80 days or something crazy like that, assuming we had more values in our data set, then we could say there's more variability, there's more differences among the different numbers of iPads sold. Okay. So now let's move on to relative frequency distribution tables. So relative frequency distributions are really, relative just stands for the percentage. So now we're looking at the percentage, not just the raw quantity or the raw frequency. And these are great for understanding the relative magnitude of differences between categories. So just to show you how to calculate the relative frequencies, you take, and here's the equation up at the top, or the formula. So F with a little subscript I. F represents the frequency for the value of interest. That's what the little I represents. So F is the frequency, I is for the value of interest. Then you're dividing that by either n lowercase or n uppercase. If you're working with a sample, the correct notation would be a lowercase n. If you're working with a population, the correct notation would be an uppercase n. In this case, we're working with a sample of 50 days. So 50 will be the denominator in this first part here. Then you take that value, so the frequency for the value of interest divided by the total frequency of all of the values in the data set, and multiply that by 100. And you can see in the far right column here, I did that for every single different value in our data set. So the first one we're looking at for 0 sold per day. There were 5 days where that happened. 5 out of 50 days gives us 0.10. 0.10 times 100 gives us 10%. Then if you move down, 8 out of 50 days, we sold 1. So 8 divided by 50 is 0.16, multiplied by 100, and you get 16%. So this just gives you a nice way to display the different percentages associated with the different values in your data set. And you can check your work by making sure that when you add up all of your percentages, you get something close to 100, at least within rounding error, because this represents that 100% of the values in your data set were represented in this table. Now, a great way to display the relative frequencies is that you can put them into a pie chart. So pie charts are only appropriate for displaying parts of a whole for a single variable, and that's exactly what we're looking at here. Now, I want you guys to keep in mind that when you display any kind of table in a presentation or a report, you don't include the calculations in the final version of the table. But I showed them here just to demonstrate where those numbers came from and to give you an easy, concise way to find where those numbers came from. But you can see the difference between these two tables. I just report the final values in the nice, pretty, ready-to-present version of the table. And if you look at the pie chart, you can see that it's labeled, color-coded. 0 is right here, so 0 days where we sold 0, 10% of the days we sold 0 right there. And then you can just follow the color coding all the way around. Again, this is important. Pie charts are only appropriate for displaying parts of a whole for a single variable. And your pies better add up to 100%. Okay, now let's move on to a situation where you cannot just display every single value in your data set from lowest to highest in its own row. Because remember, the whole point of doing frequency distributions is to simplify your data. Well, if you have a really large range in your data set, so if you have a value that's really small and a value that's really large, it's not going to be a very pretty table if you represent the full range of those values. So you can group scores together, and that helps simplify the data. Now, before I get into group frequency distribution tables, it is worth mentioning that when you group values together and put them in a table, you do lose some rich information because you no longer know exactly how many times each score is in your data set. So you cannot do calculations using a group frequency distribution table, and sometimes you don't really understand the full nature of your data because you are grouping things together. Okay, so if you look at these steps for creating a grouped frequency distribution table that is easy to interpret. That's a key word. You can group however you want, but you want to follow these guidelines if you want something that's actually easy to understand. So the first guideline is to make sure that you have a manageable number of groups. So you want to have a small enough number of groups to where your table is not crazy, but you still want to provide adequate detail. You don't just want to split it in half and have half in this line and half on this line, and you're just going to lose so much information. So a nice guideline to make sure that happens is to use the 2k greater than or equal to n or n rule. So if you see, we've got 2 to some exponent, which is represented by k. So you're going to find which exponent of 2 gives you a final value that's greater than your sample or your population size, whichever one you're working with. And then once you find the exponent of 2, it gives you a value that's greater than your sample or your population size or equal to it. You know the approximate number of groups that you can have in your table that'll maximize the detail but also minimize the confusion. Then the next step, you want to figure out how wide do my groups need to be to achieve that approximate number of groups. And to do that, you find the largest value in your data set, subtract by the smallest value in your data set, and divide by that k that you found before with the 2k greater than or equal to n rule. Usually you're going to come up with a pretty ugly number for this. And remember, we're all about simplicity. So you'll take that ugly number and you'll round it to a multiple of 2, 5, or 10, numbers that are easy to count by. Then you want to make sure as you go through and create your table that the lowest score in each group is a multiple of the width that you just decided to use. That way, whenever somebody looks at your table, it's pretty clear to them the width of each of your categories. And you want to make sure that all of your categories are the same width. And you also want to make sure that you include the full range of scores in your data set without any overlap. So there shouldn't be a value in your data set that falls into more than one group. So that's referring to it being mutually exclusive. But you also want it to be all inclusive. You cover the full range of scores in your data set. So remember, I said that a grouped frequency distribution table is most appropriate when you have a really large range of values in your data set. If you look at this data up here, you'll see that that's the case. So this data is looking at 20 Apple stores in Australia. So you'll find that there's 20 numbers here. And each number represents how many iPads were sold in the past 50 days for that particular store. So this first number, this 120, that means in the past 50 days, this particular store sold 120 iPads. So looking at this, we can see that the smallest number in our data set is the 32. So one store sold 32 iPads in the past 50 days, and they sold fewer than any other store in Australia in the past 50 days. The store that had the highest or the most number of iPads sold in the past 50 days sold 219 iPads. So we have a range from 32 to 219. If we tried to create a frequency distribution table where every single value from lowest to highest was represented on its own row, we would have a really, really long table that didn't simplify anything. So we need to create a group frequency distribution table using the steps that I just discussed. So let's start with the 2k greater than or equal to n, and I have lowercase n here because we're calling this a sample of stores. We're just looking at Australia, not every single store. And let's say that we are interested in every single store. Okay, 2k greater than or equal to n rule. So we've identified the sample size as 20 stores. So what exponent of 2 will give us a value that's greater than or equal to 20? Well, 2 squared is 4. That's not cutting it. That's not greater than or equal to our sample size of 20. 2 cubed is 8. That's not going to make it. 2 to the 4th power is 16. Still not greater than or equal to our sample size of 20. 2 to the 5th power, however, is 32. And that is greater than or equal to 20. So we can stop there, and we've identified our k. K is equal to 5. Now, 5 is going to be the approximate number of groups, or the approximate number of rows in our grouped frequency distribution table. But that doesn't mean that that's exactly how many rows we're going to have. K is just used as a basis to figure out the group width in the next step. So depending on how you round, because we're going to round to a multiple that's easy to count by, you may have a little bit fewer or a little bit more numbers of groups than k. So if we look at the largest minus the smallest value in our data set, the largest being 219, smallest being 32, 219 minus 32 is 187. Take that, divide it by k, we get 37.4, which is an ugly number. We don't like that number. Nobody's trying to count by 37.4. So let's round it to the multiple of 10, which is 40. That's going to be our group width. So now we need to create the table. Just like before, the first column represents the values that you're interested in your data set. The second column represents the frequency of all of those values. Or in this case, we're looking at how many stores had a particular number of iPads sold in the past 50 days. Now what I usually do is I start to try to think about, okay, I know I need to cover the entire range of scores in my data set. My widths are going to be 40, so I know my first class needs to be from 0 to just below 40 to capture that low end of 32. And then I start thinking about, okay, I'm going to start with 0, and I'm going to count by multiples of my width of 40 until I get to a class that's going to capture my high end of my distribution, or 219. So I start with my first column, label it with the variable I'm interested in, and then start with the low end and count by my width. So 0, 40, 80, 120, 160, 200. And then I stop at 200 because I think about it. I'm like, okay, 200 to just below 40 would be 239. That's going to capture 219. So once I've got the low end of each different group, I'm going to go up to the top and I'm going to insert the high end of each one of my groups. And the easiest way to do that is to just think, okay, what's the number just below the low end of the next group? So what's just below 40? 39. Then go down. What's just below 80? 79. What's just below 120? 119. What is just below 160? 159. And what's just below 199? Or sorry, what's just below 200? 199. There we go. So that makes sure that you don't miss anything, you cover the entire range, and there are no overlaps. So you're not going to have any stores that fall into multiple categories. Because if you sold between 0 and 39, you didn't sell between 40 and 79, for example. So if we're just looking at this simplified version of our data, we can see that a select few sold 200 plus iPads. But there were many in the low end who sold less than 120 iPads over the course of 50 days. And that's a lot easier to see than when you're just looking at all of the numbers on a screen that aren't placed into a nice, neat table. An even better picture of the data comes when you place it into a histogram. So I used a histogram because the number of iPads is a ratio variable. And if we look at this, it's the same type of system as before. You have your values of your data set, and your data set represented along the x-axis. And then the height of each bar represents the frequency of each of those values. And here we can see that we have a unimodal distribution. Most stores sold between 40 and 79 iPads in the past 50 days, and it is a positive skew, meaning that the bulk of iPads sold were in the lower end of the distribution, with a couple of stores that sold a lot more than everybody else. Now, another way that you can display data that has a large range of values without losing that richness of information. So remember, I mentioned that with grouped frequency distribution tables, you're not representing every single value in your data set because you're collapsing them into groups. A stem and leaf diagram does represent every value in the data set and can still simplify your data. So you can look at the description of how a stem and leaf diagram is created, but I find that it's much easier to just look at an example. So looking at the stem and leaf diagram, you can see that the leaf is usually the last digit. The leaves are the columns following the first column. These are our leaves here. And then the stem represents everything before the last digit. Now, you may look at this and say, wow, there's 20 different rows here. There's 20 stems and leaves. Well, stems with their own leaves next to them. Well, that's better than 188 rows that you would need to represent the full range of values in this data set. So although it is a little more complicated and a little bit bigger than the grouped frequency distribution table, it's great because you aren't losing any information. Every single score is represented. Let me demonstrate. So that top row, you see this 3, 2, and a 5. Well, the 3 stands for all scores in the 30s. And we have 2 of those. We have a 32 in our data set. There it is. And we have a 35 in our data set. So that top row represents 2 scores, one of 32, one of 35. The next row represents all of the scores in our data set that are in the 40s. So we have one score that is 40 and another score that is 45. And you can find those in the raw data. The next row represents scores in the 50s. So 52, we have a score of 52, and we have a score of 55 in our data set. And you see that trend all the way down. So getting down to the bottom here, the 21 represents the scores in the 210s. So we have one score that's 219. That's represented along that bottom row. Now the really neat thing about the stem and leaf diagram and how it corresponds to the histogram is that if you flip that histogram over, so if you turn it to the right, if you turn it clockwise, well, first of all, we can see that P shape emerged. Remember the positive skew thing? But you can also see that the shape of the histogram, if you turn it on its side, mimics the shape of the stem and leaf plot. So, from 0 to 39, you can kind of like see the bars. Like it's like, woo, it's kind of loopy starting at the low end, and then as it gets to the higher end, it starts to taper off a little bit, dips completely down between 170 and 190, and then picks back up in the 200 to 239 range. You can see there. Just kind of a nice comparison of how the stem and leaf diagram, the shape mimics the histogram, and you don't lose any information. So now let's move on to a scenario where you have two variables. So before, we were just looking at one variable. If we were, counting how many iPads were sold, or like in this case, we were looking to see how many iPads were sold across different stores. Now we're going to look at two separate variables. And for the joint frequency distribution table, it's also called a contingency table when you're doing a frequency distribution table for two variables. You'll have one variable that's represented on a row, and then you'll have one variable that's represented on the column. So here's an example. Let's say the Apple Store is considering implementing a no check policy before Black Friday. So they aren't going to take checks from Black Friday to Christmas. And they're doing this because checks take time to process. They want to eliminate long lines and waiting. Before they do this, though, they do collect some data to anticipate how many of the big spenders pay for their purchases by checks. And not only that, they know that they want to please their female customers. Their female customers tend to spend more money than anybody else. So they also want to make sure that they aren't going to be alienating females at Christmas time by making sure that females aren't more typically paying with checks than any other group than males. So one thing I want to point out, in almost every case when you're looking at data, you're looking at a sample of data. You're not looking at every single piece of information, and it's impossible to predict with 100% accuracy what's going to happen in the future based on data collected in the past. But it's better to try to make informed decisions using data, even though there's limitations, than it is to just do it blindly. Okay. So if we're looking at the joint frequency distribution table, so our data is over here on the left, and this is sex and payment type for the big purchases on the Friday before Black Friday. So we collected data the Friday before Black Friday to anticipate what would our Christmas rush look like, what kind of payments would people be using. So this first customer, in the top row, was a female and paid with cash. The second customer was a female and paid with credit, all the way down to that last person who was a female and paid with cash. Looking at the data in this form isn't very useful. It's hard to really detect the trends in the data. It is much easier to detect the trends in your data if you put it into a joint frequency distribution table. So you can see that we have broken up the groups of interest, so females versus males, and then we count how many of each group have the different types of payment method. So we've got our groups of interest along the columns, and then the different types of payment along the rows. So just to break this down, 4 females paid with cash. So if we go over here and look, we see, okay, that first female, that's paid with cash. We go down, we see, let's see, another female that paid with cash, another female that paid with cash, and then the bottom, that female paid with cash. So that's where that 4 comes from. Then you can see that there are 6 females in our sample who paid with credit, 3 females who paid with check, adding up to 13 females in total. We have 3 males who paid with cash, 2 males who paid with credit, and 2 males who paid with check, giving us 7 total males. Now that last column, the total, that represents, so if you look at the 13 and the 7 along the bottom, that represents the number of females and males regardless of payment method. Whereas if you look at the column, the final column on the right, that total represents the number of people in our sample who paid with each different payment method regardless of their sex. So we have 7 people who paid with cash, 8 people who paid with credit, and 5 people who paid with a check, not thinking about whether or not they're a male or female. Then this bottom number right here is the 20. So we have 13 plus 7 13 females plus 7 males gives us 20 people in total. 7 who paid with cash, 8 who paid with credit, plus 5 who paid with a check gives us 20 total as well. So when we're looking at this table, we could say, okay, well, there's not very many big spenders who pay with checks, right? Only 5 out of all 20 paid with checks. You could also see that slightly more females use cash and checks. So we could anticipate that if we stop taking checks, we're going to have equal alienation. So, the 3 and the 2 are pretty similar. We could also look at this and assume that 3 times more females paid with credit, 6 versus 2. What's wrong with this interpretation? Think about it for a second. So saying, 3 times more females pay with credit and almost the same number of males and females pay with check is misleading because there are more females than males in this sample. Now, it's revealing that there are more females who were big spenders on Black Friday, but this does not accurately portray the differences in payment types based on sex because there's more females in our sample. Of course, there's probably going to be more females for each different category of payment. Despite that limitation, I placed the data into this bar chart here. And you can see that you color code the bars to represent each group. So males versus females, different colored bars. And then you just plot as usual for each group. So you can look at the table and see how it corresponds with the graph. So the red bar represents females. How many females paid with, let's look at the first group, cash, 4. The red bar above cash corresponds to a 4 along the frequency. And you can see how those two correspond with one another. So by looking at this graph, we're looking at this, and the thing that jumps out to me is, oh my gosh, way more females paid with credit than males. But remember that limitation. Remember that, of course, more than likely, regardless of any preference among payment types for males versus females, you're going to see taller bars for females because there are more females in the sample in general. So if we convert this joint frequency distribution table into a joint relative frequency distribution table, you can convert the frequencies into percentages, which can be useful for making comparisons as well. But the limitations that I discussed earlier still hold, and I'll show you how to account for that here in just a second. So just like before, when you're looking for joint relative frequencies, or that's really just a fancy word for percentages, relative stands for percent essentially, you will take the frequency for the group of interest, so that's the little f subscript I, divided by the total number of frequencies for the entire data set. So the sample size or population size. In this case, we're working with a sample. And then you multiply that by 100. So for this first cell down at the bottom, the females who paid with cash, you can look above in that table and you see that 4 females out of 20 total people in our sample paid with cash. So that gives us 0.20, 4 divided by 20, multiply that by 100, and you get 20%. Let's move on to the males who paid with cash. So looking above, we can see that 3 males paid with cash out of 20 total people in our sample. 3 divided by 20 is 0.15 times 100, 15%. Now let's jump down to the bottom row here, these totals. So we can look at the total number of females. 13 out of 20 in our sample were females. 65% of our sample was female. Males, 7 out of 20 were males. 35% were males. Now, if you look at the bottom right side here, you can see that 100% of our sample is represented in total. That's a good way to check your work. When you add up the total for each payment method, despite what sex the person was, you should get 100%. So going back up to that top row in the far column, you can see that 7 people paid with cash out of 20. That gives you 35%, just for example. Now, you can also have a joint relative to group total frequency distribution table. And this strategy overcomes the limitations associated with having a drastically different sample size for your two groups that you're comparing, because it controls for the fact that in this case we do have more females than males, because you're comparing each group, well, each subgroup, so each payment type by sex, to the number of people who are that sex. So instead of just saying I'm going to divide everything by 20, the total number, each group, the values will be divided by the total number of people in that particular group. So when you look at the formula for this, you'll see a little bit of a difference, right? Before, when we were dividing by the total, we had the frequency for the group of interest divided by the total number of people in our sample. Well, now we've got the frequency for the group of interest divided by the total number of people in the particular group that we're looking at. And then you multiply that by 100 still to get your percent. So let's go ahead and look at the top left cell here, looking at females who paid with cash. So we've got 4 out of 13 females, whereas before it was 4 females who paid with cash out of the total 20. Now we're limiting our denominator to the total number in that particular group. So 4 out of 13 females paid with cash. 4 divided by 13 gives us 0.3077. Multiply that by 100. You get 30.77% of females paid with cash. Whereas before, this number, this 20%, says that 20% of the entire sample were female who paid with cash. This says 30.77% of females paid with cash. So think about the difference between those two interpretations. You'll also see that each group is going to represent the joint relative to group total frequency is going to be 100%. This number represents the total number of females compared to the total number of females, multiplied by 100, gives you 100% of the females. One thing I do want to point out is that the totals in the far right column do not change because those are looking at the total number of people in the sample with each payment method without taking into account which sex that person was. So let's compare these directly. It is, real quick before I compare them, it's worth noting that the joint frequency distribution bar graph, so the one on the bottom left here, looks exactly the same as the joint relative frequency distribution bar graph that you saw 3 slides ago. So if we go back here, this picture looks exactly the same as this picture when we just change the frequencies to percentages. And you think about it, 4 out of 20 females paid with cash, 4 out of 20. That corresponds to the 20% here. So it makes sense that once you convert the the frequencies to relative frequencies, it doesn't change the shape of your distribution. But once you start comparing it to your group totals, it does change the shape of the distribution. Okay. So if you think about it, the joint relative to group total frequency distribution, so the second one that you see here, when we took into account the difference in number of females versus males, it is far superior to the joint frequency distribution and the joint relative frequency distribution in cases when you have a different sample or population size, which we do here, right? We've got more females than males, so we need to take that into account when we figure out our relative frequencies. Take a minute to examine the difference between the joint relative and the joint relative to group total frequency distribution tables and bar charts that you see on the screen. So again, you should see that by comparing the frequency within a particular subset of a group to the group total, instead of the entire sample or population, you control for the fact that one group is larger than the other. So in other words, by comparing the frequency of females who paid cash to the total number of females, instead of comparing the frequency of females who paid cash to everyone, males and females, you control for the fact that there are more females than males. There are more females in this sample, so of course, again, we would expect there to be higher relative frequency of payment types for females compared to males, regardless of any sex-based preference for payment type. So go ahead and look at the first table and chart. At first glance, it appears that females pay cash 5% more than males. But this is not true. These relative frequencies are based on the total sample. What the table actually indicates is that 20% of the entire sample were females who paid cash, and 15% of the entire sample were males who paid cash. If you're trying to examine sex-based payment preferences, this table is not going to be very useful, that one on the left. If you look at the second table and chart, so the one where we're controlling for the difference in number of females versus males, you can see that 30.77% of females in the sample paid with cash compared to 42.86% of males who paid with cash. You can accurately state that 12.09% more males paid with cash. So in this situation, you can see that there appears to be a slight preference for cash among males compared to females. The first table and chart inaccurately suggest that more females prefer cash, but the second table and chart reveals the true difference, that a larger percentage of males prefer cash than females. A similar trend emerges if you look at checks. So if you look at the first table and chart, it appears that females pay with checks 5% more than males. But this is not true. As you can see in the second table and chart, after you control for the fact that there are more females than males in the sample, males pay with checks 5.49% more than females. Now let's take a look at credit. You can see that both sets of tables and charts suggest that more females pay with credit than males. However, the first table and chart artificially inflate this difference because there are more females to begin with, whereas the second table and chart control for having more females in the sample and show that there is not as drastic of a difference in the percentage of males versus females who paid with credit. So if you consider the original question, who will Apple alienate if they stop taking checks at Christmas time? You could look at both tables and charts for answers. So according to the second table and chart, males will be slightly more inconvenienced if Apple does not allow checks for payment. And again, this is a projection based on the data that we collected. It's not 100%. We know this is going to be the case for sure. Well, you can look at the first table and chart and see that the majority of customers are female. So maybe you're not so concerned about male reactions and male alienation. However, as you can see in the second table and chart, there's not much of a difference in check preference between males and females, so you're nearly equally at risk of alienating males and females if you stop taking checks. You can look at the first and second table and chart and see that 25% of all customers paid with checks. You might want to think, is that too many to risk upsetting? Maybe you don't want to try to alienate 25% of your customers or upset them in any way. Now you can consider the potential impact of such an inconvenience. Will 25%, if this sample represents the population and if this data represents what's going to happen at Christmas time, will 25% of customers be upset if they're forced to use another payment method? Will they be so upset that they will go to Best Buy instead? Will the time saved by not taking checks and having faster checkout times and shorter lines be worth it? Long lines scare customers away, so you have to think about those things when you're making that judgment call. So although both tables and charts are useful, it's clear that to determine sex-based preferences, you need to use the joint relative to group total frequency distribution table and chart. Remember, you have to control for the difference in sample sizes for males versus females. However, it's also useful to use the joint relative frequency distribution table to see the differences in group sizes. So I show you this so that you understand how sometimes data can be presented in a misleading way, and you need to be careful and think about what the tables represent that you look at, especially when you're given pictures, graphs, and charts, and not access to the figures. It's really easy to mislead people. So I guess that's where the lies, damned lies, and statistics saying comes from. It's not really the stats that are lying, it's the people who are manipulating them that lie. Or mislead, I guess is a better way to say it. Okay, Let's move on to time series data. So you should remember in the previous lecture we talked about the difference between cross-sectional and time series data. Time series data is data that's collected over a period of time, and you want to parse out the differences across time in your data. Whereas cross-sectional, the data we were looking at before, is just a snapshot of data collected at either one period of time or over a period of time where you're not really outlining the differences in time, and it's not a big area of concern when you're looking at your data, the differences across time. So remember from slide 11, you had the first three columns there looking at each day of one specific week and how many iPads were sold each day, and then the relative number of iPads sold, or the percentage of iPads sold for that particular week each day. Well, now I added the cumulative relative frequency column, which indicates the percentage of sales on or before a certain day of the week, or in other words, the percentile of sales for any given day of the week. So cumulative relative frequency distributions, or percentiles, can also be used to display percentages at or below a certain score. So for instance, if we were looking at SAT scores, and I said I'm at the 90th percentile for SAT scores, that means that 90% of test takers scored at or below my score. Or in other words, I scored as well or better than 90% of test takers. So in general, the percentile represents the percentage of values that are at or below a particular score, or the percentage of, in this case, sales that happened on or before a certain period of time. So to get these percentiles, you need to start with the percentage for the earliest time period in your data, or if we were looking at values in our data set, the percentage associated with the smallest value in our data set. Regardless, we're starting at the top, we're working our way down. So what percentage of sales happened Monday or before this week? 0%. Then we move on to the next one. You add the percentile for the earlier number to the percentage for the value of interest. So 0 plus the percentage for the value of interest, 10.53, gives us 10.53. So we can say that 10.53% of iPads were sold on Tuesday or earlier. Now let's move down to Wednesday. We add the percentile for the day just before, 10.53, to the percentage for the day of interest, 10.53, you get 21.06. So you could say that 21.06 of all the iPads sold this week were sold Wednesday or before. Moving on. Take the percentile for the value that happened just before the value of interest, so 21.06, plus the percentage for the value of interest for Thursday, 15.9 or 15.79. Add those together, you get 36.85. So we could say that 36.85% of all the iPads sold this week were sold Thursday or before. Moving on. Take that percentile for the value you just found, 36.85, add it to the percentage to the next value, the one you're interested in now, and you get 36.85 plus 15.79 equals 52.64. So we could say that 52.64% of all iPads sold this week were sold before or on or before Friday. So more than half of iPads were sold before the weekend. You can think about it that way. Moving on, we take that 52.64%, the percentile for Friday, add it to the percentage for the next highest value, or the next later value, which is Saturday, to 21.05. You get 73.69. Now I want you to try to say out loud in kind of plain English, the way I've been doing it, the interpretation of this 73.69. Feel free to pause it and give it a shot. Okay, so hopefully you said something along the lines of 73.69% of all iPads sold this week were sold on Saturday or before Saturday. Then when you get to the final value, you add the percentile for the next earliest value to the percentage for the value of interest right here. So the percentile for Saturday plus the percentage for Sunday, 73.69 plus 26.32 gives you 100.01%. So we can say that pretty much within rounding error, 100% of all iPads sold this week were sold Sunday or before, because that captures the entire week from Monday to Sunday. One good way to check your values, make sure you didn't make any mistakes, is to make sure that when you get to the percentile for the highest value or the latest value in your data set, that equals the sum of your percentages in the column right next to it. So just to answer a couple of questions using this table, people really do get confused about percentiles a lot. That's why I keep explaining over and over again what the interpretation is. So if I ask you what percentage of the week's iPad sales happened on Saturday, I'm not asking you for a percentile. I'm asking you for a percentage. So you could just go to the row that represents Saturday, look at the percentage, and tell me 21.05 of the week's iPad sales happened on Saturday. But if I'm looking for a period of time at or before a specific day, so if I say what percentage of the week's iPad sales happened before the weekend, so in other words, on or before Friday, there's that 52.64%. That represents the percentile. Now, the primary reason that I calculated these cumulative relative frequencies was because these are the numbers that you present in an ogive. So you're going to be looking at an ogive in the next slide, and that is based on the final values that you see in this last column. So here's our ogive showing cumulative increases or decreases over time. And you can go back and you can say, okay, the day of the week, Monday. Remember, that was 0, so that represents 0. Then we go on to Tuesday. Whoop. We had 10.53%. Then Wednesday, representing 21.06%, and so on and so forth. So the height of, now this time, the line represents the frequency of interest, in this case the cumulative relative frequency, and it's above the respective value of interest or the day of interest along the x-axis. So it's important to note that an ogive shows cumulative increases or decreases over time. So you can look at this and you can see that the rate of change increased over the weekend, for example. But an ogive is only appropriate for variables with frequencies that can be added up over time, not for frequencies within separate, unrelated units of time. So for instance, you wouldn't want to use an ogive to display the number of students born each month of the year. You'd want to use a bar chart for that. So thinking that ogives represent cumulative increases or decreases over time, it's building upon the times before it, you're not going to have any dips or peaks in this data. It's going to be a constant flow. You're not going to have a drop off and then it goes back up, because we're looking at cumulative increases or decreases over time. They build upon the time before it. So you're never going to have, for instance, a percentile for Saturday that's less than the percentile for Friday, because the starting point for the percentile for Saturday is the percentile for Friday. So let's move on to line graphs. So line graphs are different than ogives because the height of each point in the line indicates the frequency for that particular time period, not the cumulative frequency for that time period and all time periods before, or the, cumulative frequency for that score and all scores before, depending on what kind of variable you're looking at. So maybe the manager at the Apple store wants to see if having more geniuses is related to selling more iPads over the course of the week. Or maybe the manager at the Apple store wants to see if they're staffing enough geniuses to keep up with the demand for customers who need help setting up their new iPads in the store. This graph, if you look at it, and let's kind of break it down really quickly. So the same thing as before. You have your variables represented along the bottom, or the values for your variables represented along the bottom. And then you have your frequencies represented along the y-axis. Well, in this case, we are looking at multiple variables across time, not just one variable. So these two lines represent the two different variables that we are looking at. So we're looking at each day of the week. Number of iPads sold is represented by the red line. Number of geniuses is represented by the gray line. And this is a great way to display data when you're looking at two different variables across time. To use two color-coded lines, and then you have your timeline along the x-axis. Well, this graph makes it look like there's not much of a relationship between iPads and geniuses on staff, and it suggests that there's always far more geniuses on staff than iPads being sold each day. This graph actually underrepresents the fluctuation in iPad sales. So if you look at the raw numbers in the data or in the frequency distribution table, you can see there is some variation. But when you look at the line graph, it looks like there's not much fluctuation or variation in iPad sales. It looks like kind of a straight line. Well, this is because the frequency metric along the y-axis is based on really large numbers. So if you go, 0, 5, 10, 15, 20, 25, well, the only variation that you have in number of iPads sold ranges from 0 to 5, and that's not adequately captured in that y-axis. That y-axis is appropriate for geniuses who do have a large range of variation, but not so much for iPads. So this graph is not a very adequate description or representation of the data. This graph is much, much better. This graph is different than the previous because there are two sets of y-axes that represent an appropriate scale of frequencies. So the left side represents the frequencies for iPads. So there's a smaller range, and that's represented there. Then the right side of the graph represents the frequencies for geniuses. So there's a larger range in that frequency of geniuses. You can see that represented. Now you can see that having more geniuses is related to selling more iPads over the course of the week, and they are staffing at levels comparable to changes in iPad sales over the course of the week. This graph makes it look like there is a relationship between geniuses on staff and iPads sold, now that we've compensated for the fact that there's a different range for each variable. And this graph also represents the fluctuation in iPad sales because the frequency metric for iPads on the left is based on the small numbers. So this is a better representation of the relationship between these two variables. Speaking of relationships between variables, now we're going to look at scatter diagrams, which I mentioned earlier is the basis for correlation analysis when you're looking at the relationship between two variables in a single group. But we're not going to talk about correlation, just the pictures of the data that you would use for a correlation. So a scatter diagram, again, displays the relationship between two variables. Remember, x is kind of a placeholder for a variable. Well, when you have two variables, you can refer to the first variable as x and the second variable as y. So we're looking at the relationship between x and y in a single group. We're no longer looking at frequencies anymore. We're going to be looking at raw scores for one individual, two scores for each individual across a single group. And that'll make more sense as we look at several examples here in a second. So there's three characteristics of a relationship. The first is form, so kind of the shape of the graph when you plot x and y. Keeping in mind that when you plot a scatter diagram, you're still going to have the values for your x variable along the x-axis, but now y is going to represent the values for the other variable, not the frequencies associated with each value in your x. Okay, so the form is kind of like the shape, but only when you have two different variables plotted in the same graph. You can look at the direction of linear relationships, so positive versus negative. We'll talk about that in a minute. And then the strength of the relationship, so how consistent is the relationship between the two variables? Is there a predictable pattern where, increases or decreases in one is related to a constant increase or decrease of the same magnitude of the other? So let's talk about form first. So when we're looking at form, we want to know what shape do data points form when we plot both of our variables on a scatter plot. Well, if there's no relationship between the two variables, you really won't see a pattern emerge in your scatter plot. But if there is a relationship between your two variables, typically you'll either see a curvilinear pattern or a linear pattern. And let me show you the difference between those. So curvilinear forms can have an inverse U shape like this, or a U shape like that. And there's a relationship here, but it's not a consistent change. So as x increases, it's not a consistent increase or decrease in y. It's like as x increases, y increases to a certain point, and then as x increases more, y starts to decrease. That's what you can kind of see here. So typically, your values for the x variable are listed along the x-axis and then y listed along the y-axis. And one thing that I want to point out, A lot of times, when you're looking at the relationship between two variables, it's not 100% clear which variable comes first, which variable is the predictor and which variable is the outcome. Or in other words, which variable is the independent variable or the dependent variable, if you're familiar with research lingo. So we try to strive to assign x to the variable that we think is the predictor, or what precedes the other variable y. So in this example, research suggests that stressful work events predict performance appraisals and performance in general. So that's why stress was assigned to the x-axis, performance assigned to the y-axis. But now that I mentioned that, be careful, because just because two variables are related does not mean that one causes the other. We haven't measured every single thing that can have an influence on performance, and there can be other confounding reasons why you see this example or this pattern of relationships. So correlation does not equal causation. It's just a relationship. But before we get into the nitty-gritty of picking this apart, I just want to make sure that you understand how to create a scatter plot. So if we're looking at this, and I color-coded for you, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different employees in this data set. And that corresponds to 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots in our scatter plot. So each dot represents one row, one person in this case, in this data set. And what you do to plot this is you find the value for x along the x-axis, and then you go up to the corresponding value for y on the y-axis, and you put a dot there. Again, each dot represents one person. Each person gives you 2 scores. So this first person said that they rated themselves as 0 stressful work events in the past quarter, and they had a performance appraisal score of 50. And you can see the blue box in the table and the blue box in the graph represent that same person. So you would find 0 along the x-axis, go up to 50 on the y-axis, boom, dot for that first person. If you go down a little bit to my yellow person here, they had a 25 stressful work events in the past quarter. Poor thing. And their performance appraisal score was a 100. So their dot, you go over to around 25 on the x-axis, go up to 100, and you find them there. So we're looking at this plot, and this is actually a commonly studied phenomenon in IO psychology. You can see that there's kind of a sweet spot for stress. So if you look on the low end of stress, you tend to not perform as well. Maybe there's not enough stress to motivate you, and you're just kind of, just hanging out and not doing much. There's not a whole lot of pressure. When you get to the opposite end of the spectrum and you're extremely stressed out, performance is also low because you're just overwhelmed and you can't perform very well. But this sweet spot in the middle is just enough stress to be motivating and not too much stress to completely derail your performance. So that would be a curvilinear relationship. Here's another curvilinear relationship. This is the more U-shaped relationship. So looking at the relationship between age and car insurance premiums. When you're really young, you're considered high risk. So when you're younger, you tend to pay higher insurance premiums. And this is, all other things being held equal. We're assuming there's no DUIs or you don't drive a crazy expensive car. So all other things being held equal, typically the younger you are, the more insurance you pay. To a certain point. Because once you get to be elderly, your insurance premium goes up again because I guess they assume you're senile or you can't see, or maybe you're just so old that you don't care if you get into a car accident and die in a fiery blaze of glory because you're close to death anyways. That's morbid, but it's an example. So your insurance premium is really high when you're super young and really old, and then there's that sweet spot in the middle where your car insurance premium bottoms out because you're at the age of being responsible, but you're not so old that you're starting to deteriorate and you can't see very well to drive. Here's a linear relationship. So where there's a consistent increase in X or Y as there is an increase or decrease in X or Y. Or in other words, there's a consistent, in this case, increase in Y as X increases. That gets at direction, which we'll talk about here in a little bit. For now, just know that it's linear if you have a diagonal line, just a straight line that goes either up or down. That would be a linear relationship. So looking at this, you can see consistently As you study more, your quiz grade improves. There's no dip in your line here in your scatter plot. Here's another linear relationship. As you do more cardio, consistently there is a decrease in your percentage of body fat. You can see the line emerge when you plot your data. Now, I've already alluded to direction, but here is an explanation of direction of relationships. If you have a positive relationship, that means that x and y tend to change in the same direction. So, as x increases, y increases. As x decreases, y decreases across all of your data points. If you have a negative relationship, that basically means that you have an opposite effect. So, higher scores on x tend to pertain to lower scores on y, and lower scores on x tend to pertain to higher scores on y. So back to the time studying and quiz grades, this would be considered a positive relationship. You study more, your quiz grade tends to improve. When you plot it out, you also see that there's an upward slope. Then there's negative direction. So remember that's, it's changing in the opposite way. So as you do more cardio, your body fat tends to decrease. And when you plot it out in a scatter plot, you can see a downward slope on your scatter plot. Now let's talk a little bit about strength. So there's 3 different levels of strength. Strong means it's very consistent relationship. So if we're talking about a positive strong relationship, as x increases, there's a consistent incremental increase in y across everybody in your data set if you put them in numerical order. When you plot it out, you can see that the data plots fit a straight line pretty well, assuming that we're only looking at linear relationships, which is what I am going to focus on. Moderate relationship, less consistent. If you look at the numbers in your data set, you don't see a consistent pattern as much. And when you plot your data in the scatter plot, it's less linear, it's kind of scattered out, but you can still identify the direction of the relationship. Now, weak, sometimes higher scores on x pertain to drastically higher scores on y. Sometimes higher scores on x pertain to somewhat higher scores on y or lower scores on y, or it's just all over the board. There's no consistency there. So the data points, when you plot them in a scatter plot, are really scattered, and you really just can't even identify the direction of the relationship. It looks like a shotgun blast went off. One way that some people think about it, if you have a strong relationship and you draw a circle around the dots in your scatter plot, it's a narrow circle. For a moderate relationship, you draw a circle around the dots in your scatter plot, and it looks kind of like a football shape. And then for weak, you draw a circle around all the dots in your scatter plot, and it just kind of looks like a circle. So the strongest strength, this is a perfect relationship. You can see that for each 500 increase in calories, you have a consistent 50-pound increase in weight. It's a perfect linear relationship. Going the other way, for every person that consumed 500 less calories, they weigh 50 less pounds consistently across all data points. And the scatter plot fits a straight line perfectly. Here's a moderate one. So if you drew a circle around these, kind of like a football, it is kind of spread out, but you can discern that it is a positive relationship. You see that upward slope. And if you look at the numbers, you see those first 3 people, they had 1 sibling, a couple of them had 1 child, a couple of them had 2. We have another person that had 1 sibling who had 3 children. We had another person who had 5 siblings, and they also had 3 children, just like one of the people that had 1 sibling. So there's not a really strong relationship between the number of siblings you had growing up and then the number of children that you eventually have, although it's slightly positive. So there's a slight trend that more siblings tend to be related to more children, but I wouldn't bet on it. Here's an example of a weak relationship. So if you're looking at the relationship between your grade in anatomy and physiology for nurses and the percentage of passing stations on this exam that they take. Not really a clear relationship, and this is actually based on past research. So you can see that if you drew a circle around that scatter plot, it's going to be a big old circle. It's not going to be a football, it's not going to be narrow, and it's hard to identify the direction of the relationship. And if you look at the numbers, you can see, and I put them in numeric order based on anatomy and physiology grade, you can see, like, if this was a strong positive relationship, as x increases, you would expect to see y increases. But check it out. It's like, okay, it increased there. Oh, it decreased. Oh, increased, decreased, increased, decreased, increased, decreased, decreased. I mean, it's just not consistent at all as you go down that table. So take a look at this. What kind of relationship is this? So if we're looking at over the past 50 days, how many geniuses were on duty that day, and what was the average wait time in minutes for that particular day? And let's say that this is all based on a particular shift, maybe like the busy shift from 11 in the morning till 7 at night. Keep in mind, we're looking at two variables. So if we're thinking about there's 50 days, we have day 1, 20 geniuses, average wait time 0.6. Day 2, 22 geniuses, average wait time of 1.2. And you have 50 pairs of scores in this data set to represent each day. So again, take a look at this scatter diagram and tell me what kind, well, tell yourself, do you think it is a strong, a weak, or a moderate relationship? Do you think it's positive or negative relationship? And it is linear, I'll tell you that. So hopefully you identified that this is a strong negative relationship. So in plain English, and plain English is important, you need to be able to describe your scatter diagram results in plain English. And usually I try to use the word tends to because that helps imply that we're not inferring causation. So in plain English, there tends to be a shorter wait time when more geniuses are on duty. This doesn't necessarily mean that more geniuses guarantee shorter wait times. Remember, be careful about correlation not equaling causation. All right, so I just crammed your brain full of tons of very useful information. When it comes to digesting this information, hopefully this table proves useful. You will be expected to look at different scenarios and identify what type of graph and what type of table is the most appropriate way to display that data. Because this class isn't just about memorizing things. You can use this as a resource in the future if you're ever given a situation where you need to present data in an understandable and clear fashion. You'll know which type of table or graph is useful. So hopefully you are able to watch this lecture. Again, if you want to watch it, watch parts if you want. The glory of flipping a class is that you have this lecture at your disposal. You can pause it, you can rewind it, you can watch it multiple days. Do it however works best for you. And this video should prepare you for all the assignments based on how to display data.